That's loud. Those who came in, if you didn't grab one of these, there's some on the back. Otherwise, I have cut some extra up front to sit in any maroon marked seat. Grab one of these when you come in the back there, or I have some extra up here if you'd like. Yeah. I don't know. I'm trying like
not as good as the old one, but yeah,
trying different angles and things
still
like
kind of
that.
fuzzy, isn't it?
Yeah, that's the only button that's on there. I looked over.
Yeah.
Okay. I just let you know.
So I appreciate it.
Okay. I'm last time.
Fine. Yeah.
Okay.
I mean, when I start doing my own handwriting, you can't tell about the poor quality because my handwriting is sloppy enough. But looking at documents like this, it's a little bit more obvious. But yeah.
Welcome everybody, especially the freshmen back to Texas State. We'll be in class. Thanks for coming back.
Yeah, there's some questions in the back. And I have some copies up here. Sitting in each chair marked with the maroon dot that you want to sit in. Fine. All right. And if anyone didn't grab one of these from the back, let me know. I have some up here as well. Oh, sorry. All right. So welcome. Those who are here, welcome to those who are on Zoom. Hello, I'm upside down right now. Hello, those on Zoom. So this is Chemistry 1342, right? Gen Chem 2. Oh, I did not update the term here. Apologies. Not summer session. This is in fact, fall 2020. Right. So because of class size restrictions, right, things are a little different for the course in terms of how we're going to operate. So we'll talk about that today. I did have a video about kind of lecture and trying to help explain some of this on YouTube. And then there's a quiz related with kind of just some general information about the course on Canvas already. That's due by the end of the week. Okay. So before I begin with going over some things on syllabus again, any questions people have at the very beginning from what they've read, looked at, announcements I've sent?
I had a question.
Yep.
Oh yeah.
Go
Okay,
ahead.
so I was kind of confused, like over like on the Canvas website. I know that you have like the lectures posted, and then you have your recordings on YouTube. So do we look at both of those like before the class meets, or like do we look at like the lecture video on YouTube, or like what would you recommend?
Yeah. All right. Good question, and thanks. I'm glad already getting participation from Zoom. So I will record lectures and post those. Of the lecture slides, as well as then recordings of lectures, will be posted by at least the Friday before the following week. So, right, chapter 12 was all posted last week. Chapter 13 stuff will be posted by this Friday at the latest, right? Classes on Monday and Wednesday. And that's how I'll do things. So I'll at least have videos posted by the Friday before, hopefully a little bit before that, but kind of depends. And then the slides as well will be uploaded on Canvas, and those will be posted up there. And then the recordings from lectures will also be posted after lecture, right? So everything will be posted on the Canvas website. Now, videos I'll host on YouTube, but I'll have links to those videos on the Canvas website as well. You can also go directly to YouTube if you would like to check them out, and I'll get to that in a minute. But yeah, so everything will be posted. Right, we meet in Chem 100. You have to email me for any questions, right, SRY18. Office hours will be done by Zoom, right? So just email me and set up time to chat outside of class time. I'm happy to do so on an individual basis, or if you want to meet as a group, if a bunch of you study together and you all have the same question, I'm happy to do that as well. Right, Canvas, I use the username or whatever, prof_Yost. Okay, that's where the videos will be. I have sections for this class called like 1342 lectures or something like that. If you go to my YouTube channel, I also have 1342 Zoom sessions or something of that nature for lecture times, right? For the videos like this. I'll typically make lecture videos that I pre-record. I try to make them 7 minutes, 10 minutes at most. But I try to make them relatively short chunks and break them up, while Zoom meetings will be the full time in one long video, right? So if you want to watch those on YouTube, just keep in mind they'll be relatively long videos, okay? In terms of, right, the fact is the class can't all meet at the same time, right? So class is broken into 2 groups and sort of 3 for those who are taking it online, right? If you're in group A, then I expect you to come on Mondays, like I would expect you to come normally during a normal year, like 2020. Right, and if you're in group B, you're expected to come on Wednesdays, and then you should attend on Zoom as well, because each day is a new lecture, new material. I'm not repeating myself every Wednesday from what I did on Monday, okay? Wednesday is going to be different from today, and next week on Monday is going to be different, obviously, from Wednesday, right? The only time we sort of repeat days are exam days. Okay. So if there are days that are marked on the calendar for exams, if you're in group A, you come in on Monday, take your exam. Group B, you come in on Wednesday, take your exam, right? And on the other day, you just, have fun, do whatever, right? There's not going to be any Zoom meeting stuff going on and whatnot. Okay. Now, I do not want to pressure anyone to come face to face if they do not feel comfortable doing so. So again, if you do not feel comfortable, if after the first few days you're like, screw this, I see too many people sneezing on each other, or whatever, right? You don't feel comfortable coming, let me know, and I will let you take the class online. I prefer to know within the first week or two and not halfway or 3/4 of the way through the semester, all of a sudden you want to switch online, right? Now, I'm not saying that's not possible, but I very much prefer now rather than later. So if you want to, let me know and we can arrange that. If you take the class online, all right, the main differences are these participation questions like what I have for people today. Those type of things will be on Canvas and you'll have to take it on Canvas. And your exams will be posted on Canvas. If you're taking your exam online or the class online, the exam time that you have to take it is the same as regular class. So you either take it on Monday or you take it on Wednesday, but you have the same amount of time as the rest of the class and you have to take it at the same time frame as the rest of the class. Okay. Let's see here. What other differences for online? And I think that's mainly it. Homework's always been online through Sapling. If you don't have a Sapling account, please create one. There are instructions related with that in the syllabus and such, but you need to create a Sapling account in order to complete the homework. Due dates for the homework have already been posted on there, so you can check that out as well. Okay. See here, just going through the syllabus. The textbook is kind of through Sapling, if you will. It's this online textbook that is published by McMallen or something like that. And, has a lot of useful videos, a lot of useful interactive things as well. Okay. So, grading. All right. This is the breakdown of how your grade will be weighted. Okay. Right. And we'll go over some of these things individually. Right. Typical grading curve. Now, the class itself and exams and things like that might be curved based off class averages and things like that. But right. Otherwise, kind of your grading breakdown. These are the exam dates. Okay. Including the final exam, which is December 9th, right? Those dates will not change. What's on those exams could potentially change depending on how quickly or slowly we move through the course, okay? I do not do makeup exams. Instead, what will happen is if you miss an exam, your final exam will replace that exam score, okay? So if you only take 2 out of 3 exams, then your final exam will count as one of the other regular exams. If you take all 3 exams and you score and you do really bad on one and you do better on the final, that final will replace your worst scoring regular exam. Okay. So you're encouraged to take all 3 regular exams, right? So that then you have the best chance to earn the best grade in this class as possible. Okay. For the exams, you will be given something like this, okay? This sheet has a bunch of constants and things like that, as well as these equations here, and a periodic table. And that is what you'll be provided on exams. Any other type of information, equation, or otherwise that's covered in the course that's not here is not going to be given to you on the exam, typically. Okay. Again, there will be a periodic table. So that, besides your calculator and pencil, are the only things you can use while on exam. If you're taking the class online, you need to have Zoom on. Right, you need to log into Zoom, and you have the camera pointed to you, right, like this or whatever while you're taking the exam. You have to have the camera pointed. I have no idea how this is going to work if it looks at the screen, right? Pointed at like the computer screen and work area and such while taking the exam. Okay. If you're taking the exam online on Canvas, right, you have to be logged into Zoom and have like your phone or something else logged into Zoom and pointed at your work area. Okay. Quizzes, there will be a quiz for each chapter. Those quizzes will be posted on Canvas. I haven't posted chapter 12 yet, but I will be getting that up soon. And that quiz will be posted on Canvas, and you will take it there. Okay. Homework is again through Sapling, and there's some information here about setting up Sapling. Okay. And the fact that often emails from Sapling get sent to your team, and so you might want to consider adding tech support and this no reply at Macmillan to your list of like, people that you don't block, don't filter out. And then again, there's information about that here and creating your Sapling account. See here. So participation, okay. For those who are in class, right, we'll have these handouts attending today in Zoom, right? Now, simple questions you can answer throughout the course of the class, okay? And just turn them in at the end of class. You do them. Every time you attend, you get your full 5% of that grade, and any amount you get correct goes towards extra credit towards your grade, okay? And see here, final exam, right, December 9th. It's not going to be the ACS final. I don't know exactly how it's going to be. I need to talk with the other faculty members teaching 1342 if we're all doing the same final or if we're going to make our own. So I don't know exactly how that will work out, but it will not be the ACS final because of the fact that there are people that are taking classes online, and we can't do that online. Okay. I do have with me some extra face coverings. If you happen to forget one when you come, I can provide it. Please don't typically forget it because I'll run out quick. But I can provide that. If you don't feel comfortable wearing or don't want to wear a face covering, you're welcome to take the class online and not show up. Okay, because if you show up without a face covering, I'll have to ask you to leave. And again, you're welcome to always just take the class online. Otherwise, let's see here. Let me talk again. There's then the schedule that's posted in the back of the syllabus. Okay, that has a rough outline of we'll cover things, when will exams will be. So, for example, exam 1, right, are these 2 days. If you're in Group B, show up on Wednesday, take that exam. Group A, show up on Monday, you'll take the exam. Okay. Right. Similarly, right at the end of October, Group A, show up, take the exam that day. B, take the exam that day. And people who are taking the exam online will show up one of those days to take it. Okay. But yeah, that's, and so again, there's a calendar breaking down the course. I have a version of this calendar that I'm going to update throughout the semester on Canvas as well, with links to modules and quizzes and due dates and other things like that on there too. All right, to try to help keep us organized throughout the class for those who are attending in person and online. Okay. And lastly, in this course, right, part of your grade is broken up into attending supplemental instruction sessions, SI sessions. So, right, this supplemental instruction, SI sessions is 5% of your grade. Okay, the host, or not the host, your SI instructor is Riley Rogers here, and she's waving her hand for those who are online. right, and she'll come up and talk in just, well, right now, yeah, you can come up and talk right now. And then those who have asked questions online, I see your questions and I will answer them in just a minute. But yeah, Riley, come on up. Those for online, oh, this is gonna be. So you can at least stand so they can see your face, or part of your face. There
I'm
you
too
go.
short for this. Okay. Hi, everybody. Can you hear me okay? It's kind of weird talking with like the mask on. But hi, yeah, I'm Riley Rogers, and I'm going to be your supplemental instruction leader for this semester. And a little about me, I'm a biology major. I'm a biochem minor. I'm going into my senior year here at Texas State, so almost done. So if you're coming from CHEM 1342, you're kind of already a little bit familiar with how the online SI model is going to work, but I'll briefly go over it for anybody that kind of just doesn't know what it is or has any questions. So the SI program is designed with your success in mind and entails attending one 50-minute session each week for a course credit for chemistry courses, right? And these will all be held or meeting in person for any sessions. I'm going to send you out some links after you complete the sign-up survey, which we'll talk about a little bit later. But I'm going to send you out one group of links, and you're going to attend whatever session you signed up for every week. You need to attend 10 sessions before November 9th in order to get full credit for that component. Tracking. Okay. So in these sessions, we'll go over practice problems, we'll review for your quizzes or exams, we might play games, we'll have a lot of group discussion. Really, it's your time to ask me or your peers anything you might have trouble with in the course, anything you want to have deeper understanding on. We're just trying to get you to learn a little bit more about chemistry in these sessions. So I'll be working with Dr. Yost, and I'll be sitting in your sessions as well. I guess I can consider myself like part of Group A, so I'll be here in person on Mondays, and I'll be attending Wednesdays on Zoom, right, to keep in with the social distancing standards, right? To make sure all of the material that we go over in session is relevant to y'all's lecture, and you can apply it to this course, right? So I'll be holding 5 SI sessions each week and 1 office hour, and these are all going to be completely over Zoom. But first, to kick off these sessions, I need y'all to complete that SI sign-up survey. I put it in the announcements on Canvas. I posted it last Friday, I think. I'll be sending out more reminders probably tomorrow or later this week. But the survey will go live tomorrow, so Tuesday at 7 p.m. and close 7 p.m. on Thursday. So it's really in your best interest to sign up for whatever session you want as soon as you can, so it can fit with your schedule the best as possible, right? So, are there any questions so far? Any questions?
Yeah, this is gonna look
Gotta check both. Okay. Well, great. I'll be sending out more info on Canvas this week, so be sure y'all are checking your emails for all that information pertaining to that. So I look forward to seeing y'all in session. Here's Dr. Yost.
Yeah. All right. So let me just address real here. Make sure I get all these questions. So Andrew, I'm not sure. I apologize. I'm still working on keeping track of the chats and what's going on here and things like that. Not a experienced streamer, if you will, right? You know what that is. I know Twitch. All right, but so I'm not sure what questions, if Andrew, you're referring to these questions. If you're taking the course online, you'll have a set of questions similar to that will post on Canvas. If you're in Group B, then you'll just get your own set of questions on Wednesdays, okay? See here. And I guess I can post later on versions of these questions for those who want to see them. And look over them and blah, blah, blah later, but they're all fairly short, simple questions is how they're going to be designed, okay? To know if you're in Group A or Group B, that will be on Canvas. I have, every file is under the Files tab, and you can find it there. Otherwise, in the modules, I have like a course information module where I put things like the group breakdown, the seating charts, which don't really work anymore, that I'll have to update. For those, but again, as long as you show up and sit in a maroon marked chair, I'm fine. they're not going to go through and, you know, Bueller, right? I'm not going to call out names and make sure everyone's sitting where their assigned seats are, but that'll take too much of the class time. Okay? Let's see. So if you take the class online, you do not need to take the tests in person. You will take them on Canvas. And again, you have to log into Zoom while you're taking the tests through Canvas. Okay. But yeah, you do not need to come into person at all, ever, if you decide to take the class online. And again, for online people, participation is going to work. I will post quizzes for those who are online with questions like these that you will have to answer. You'll have, like, you know, 15 minutes after you start it to answer the questions or something like that. They'll be relatively short and quick. And so, yeah, if you're typically in Group A, you should try to show up face-to-face on Mondays, right? That's how right? Normally, how I do participation is that I have clicker questions and people will answer things in clickers. Because some people are taking stuff online, I don't want to make some of the class pay for that and other class not pay and things like that. So that's why I'm doing things a little differently for participation. And so yeah, so if you miss some days, that's fine. You don't have to attend every single Monday or every single Wednesday to get full participation credit. I normally drop a number of days for participation just for people who happen to miss and things like that. You know, we all have, life happens, right? And so that's fine. So attendance will be, if you're in face-to-face, attendance will be taken every day you're scheduled to show up, right? Again, just like I would in a normal semester, have clicker questions, and you'd expect to show up, answer the clicker questions, earn participation credit. That's the same type of thing that's going on here. It's just now you have to show up either Monday or Wednesday, or if you're online, you then need to take the quizzes online, okay? Or the participation questions online, right? So, all right. Anyone here, I think I've at least addressed all the questions via Zoom. Anyone here have questions about how the course is going to work? If you're, or if you decide to switch to online or anything like that. So I'll mention that, you know, I don't plan on trying to sit up here and just talk every day, because we're doing things a little differently, right? The class is scheduled to work a little differently, to where I have these pre-recorded lectures that I expect people to kind of watch and read the book and things like that in preparation for class, where during class I will highlight certain topics and we'll do just a lot of examples and example problems and go over questions and work through things and such, okay? So that is the plan for how we will do things in class and such. So please check out those videos before class so you're kind of prepared for the chapter as we cover things, okay? Yeah, I think that is at least everything covering what, how the course is going to work, what's on the syllabus and such. And if you have questions, I'm happy to answer them.
I have a question.
Yep.
It's probably a given, but I just wanted to make sure. On the syllabus, under the sapling instructions, like for the sign up, it says Patterson 001, and I know this is probably obvious, but like we sign up for yours, right?
Yeah, you do sign up.
Okay.
My apologies, yeah. So I got this obviously from MJ Patterson, that section of my syllabus, and I did not pay close enough attention to change that. Let me find where that is so I can show people. Oh, it's behind where I'm at. Yeah, no, sign up for my section, right? I don't know what the name is off the top of my head, and I'll update the syllabus with that. But yeah, do sign up for my section, right? So here, right, talked about, next page. Yeah. I'm trying to find where that is. Yeah. Yeah, not Dr. Patterson, Dr. Yost, right? So yeah, so sign up for my stuff, Dr. Yost. I only have one section. Let me over trying to here, but I only have one section of 1342. So as long as you sign up for my sapling, then you're fine, right? But sign up for Yost, not Patterson. Okay. All right. Any other questions?
I had like one last question.
Yep.
Are the lectures that you post on Canvas, or do those just act as a supplement to the lecture videos on YouTube?
So there's like, so the lecture videos on YouTube will be completely just going over topics, discussions, introducing ideas, introducing whatever things. I mean, we'll kind of see the differences today, but like, for example, right, in the lectures on YouTube, I talk, more about phases and the different phases and differences between the phases. I'm not necessarily going to talk about that today. Instead, we'll just talk about some examples and other things of that nature, right? So the idea is that the lecture class, right, the normal lecture meetings are going to be done more for examples and highlighting topics, while the lecture videos are what you would potentially expect a normal lecture to potentially be, where I'm just going over slides and going over different topics and expanding upon them and things of that nature. Okay.
Okay, so the slides are just mainly like for that, like extra, like if we need extra help or something, kind of?
Yeah, if you feel like reading the book is all you need to do, or whatever resource you want to use, and you don't want to use my lecture videos and lecture slides that are posted on Canvas, by all means, that's fine. But yeah, the lecture videos and the lecture slides are all there to help in terms of instruction and teaching the material, right? But if you feel like using another resource besides what I'm providing for you in this class, that is fine by me. I'm not paying attention to who's watching what video, right? So.
All right, thank you.
All right. So again, hopefully people feel confident and comfortable asking questions during class, anytime, or asking me questions outside of class, okay? And I'll this, right, for those seeing online, right? So if you want to address me, you can address me as Shane, Dr. Yost, Professor Yost, whatever you feel like. That's fine. My name is Shane Yost, obviously. Right. And just about myself, right? I am starting my 4th year here at Texas State. I've been teaching general chemistry now at least once every year since I've been here. I also teach upper division physical chemistry. My research here at Texas State is computational chemistry. I do a lot of computational modeling, work on computers and such all day. And so actually I have no chemicals whatsoever in my lab. So I'm the least, furthest thing from a chemist you'll find in the chemistry building. But I do know chemistry and I do enjoy chemistry. Let's see here. So what else? I'm a twin. I'm technically what's referred to, I think they're like called mirror twins. So I'm an identical twin, but I'm like a mirror. So when identical twins break apart, if they break apart too late, then they're conjoined twins, right? I was like just a little bit before that too late part that my twin brother, whose name is Shane and Sean, not very nice of my parents, but my twin brother, like the thing on the back of the head, mine goes like clockwise, his goes counterclockwise. I'm left-handed, he's right-handed. I have a dimple on one cheek, he has a dimple on the other cheek. You know what I mean? So it's in Wikipedia, it exists. I'm not making it up. But yeah, what else? I don't know. lived in Utah most of my life. I went to school in Santa Barbara, California, then out in Boston, Massachusetts, and back to Berkeley in California, and now I'm here at Texas. I have a 4-year-old and a 9-month-old, so you know, I get plenty of whining and complaining at home, so please don't whine and complain to me. If you have comments or concerns, you're welcome to talk to me about it, and I'm happy to address and trying to be as accommodating as I can in this course, especially given all the crap that's going on right now, right? But don't whine to me, just talk. Right, I grew up playing video games. I still play the occasional video games here and there. Again, I know of Twitch. I don't really watch much Twitch nowadays, but I used to. And yeah, I don't know. I'm just trying to introduce myself, say some things, hopefully make people feel more comfortable talking to me about questions or anything like that. I'm trying to, I want to be as approachable as possible. Normally I tell you to show up in my office anytime, ask me questions. Obviously during this time, given the size of my office, I prefer over Zoom, but again, I'm willing to meet and talk over Zoom anytime. Just email me and I'm happy to do so. Okay. All right. So now let's, here, share screen. So let's start talking about chemistry. Okay. So let's get started here on chapter 12, right? Chapter 12 is all about intermolecular forces and liquids and some phase changes and things of that nature. So, right, chapter 12, we start talking about phases, right? Solid, liquid, and gases. Okay. Talk about how what exists at a given phase depends on the intermolecular forces that are in that material, right? Okay. Right, these intermolecular forces, right? Again, intermolecular, as just to highlight, right, is between molecules. Okay. In 1341, you talked about bonds, right? Covalent bonds, ionic bonds, metallic bonds, right? Bonding, right? Those are typically intramolecular. They're interactions between atoms within a molecule. Here, we're talking about interactions between molecules, right? So things that are not covalently or ionically or metallically bonded to each other, but again, have different types of interactions and attractions, which are typically much weaker. Okay. Those attraction energies, those intermolecular forces, right, right, determine what phase a substance is at a given temperature. Okay. Temperature determines how much kinetic energy, a substance has. Right, the more temperature it has, the more kinetic energy it has, the more things are moving around at higher temperature they are. Okay, right. Think of it as you go out running, right? You're moving around a lot more and you feel hotter, right? Your temperature kind of heats up, right? There's this relationship between temperature and kinetic energy. Okay, right. And so at this table here, I have filled in the left side, right, where we have solid, liquid, and gas go somewhere in this table. Right, from this first part of the table here, right, if I have some substance where its kinetic energy is much, much smaller than the attraction energy, what will typically its phase be? Solid, right? So you'll typically have solid phase in the first part of this table, okay? The second part, right, we have kinetic energy is much, much greater than the attraction energies between your molecules. That's typically going to be in what type of phase? Gas phase, right? Because if you have a lot more energy to move around than the energy that's trying to hold you together, right, then you're typically expanded. And then finally, right, if your kinetic energy is similar to the attraction energy, right, last phase we have left is the liquid phase, right, and that's what liquids are like, right? Liquids, right, they have enough kinetic energy to where they can move around each other, but they don't have enough energy to break apart, right? So the kinetic energy is similar to that attraction energy, okay, right, in the liquid phase, but it's not significantly smaller or significantly greater. So again, in this chart, right, the top is solid, then gas, then liquid. Questions? So I just noticed the questions here. I guess there's some audio lag. I apologize about that. I will try to find out if there's anything that can be done about that. But it might just be kind of how the setup is in this room as to the audio lag. But I will talk with the tech support people and such to see if there's anything that can be done. The camera, I'm webcam sadly is also the camera I'm using for the document cam. So, I mean, I can try to remember when I have the slides on, point it at me. But, right, those who are online, you're seeing, I'm sharing the screen of the presentation, and that's what people in class are seeing, is that screen. But I can always, throw the camera up towards me while I have, the share screen going on, okay? But again, I will do my best to fix the audio lag as I can throughout the semester, okay? All right, so this next slide, I just wanted to highlight and remind ourselves, right, the differences between intramolecular forces, which are your bonds, and intermolecular forces, right, which are things that we're going to be talking about, dispersion, dipole-dipole, hydrogen bonding type forces, right? And we see here the melting points and boiling points for substances that are, say, covalently bonded together or ionically bonded together, right, are significantly higher melting and boiling points than things that have intermolecular forces, like dispersion and hydrogen bonding, okay, right? I mean, we're talking about 10 times higher energy temperatures, right, thousands of Kelvin for melting and boiling points versus hundreds of Kelvin, right? As a reference, right, room temperature is around like 298 Kelvin, okay? So each one of these substances, right, under the intermolecular forces are all typically either liquid or gas phase at room temperature, okay? While all the chemical bonded stuff, right, diamond, beryllium, lithium fluoride, those are all solids, right, at room temperature, okay? Okay, so question here, if a molecular solid, call it ABC, has a higher melting point than a molecular solid called, let's call it DEF, right? These are random names for solid. Which molecular solid has a stronger intermolecular forces, right? So IMF here is short for intermolecular forces. So, right, if solid ABC has a higher melting point, that means it melts at a much higher temperature than solid DEF. Which those two solids have stronger intermolecular forces? Yeah, it's going to be solid ABC, right? Because, right, having a higher melting point means it takes more energy to break your atoms apart and make them, or your molecules apart and make them start moving around each other, right? And boiling point means it takes more energy to pull the molecules apart, right? So both melting and boiling, the higher those are, that means the stronger the attraction is between your molecules, right? In order to make melting and boiling point at higher temperatures, okay? So molecular solid ABC, right, is going to have much stronger intermolecular forces than the other solids, right? Again, I put random letters here instead of giving actual examples, right? There's no A, B, C solid or something like that, right? I think there's an A atom, right? So, okay. All right. Here you go. Right. So the type of intermolecular forces I would talk about that are talk about the videos posted online and such are your dispersion forces, dipole-dipole, hydrogen bonding, and ion dipole. Okay. So Um, right, and these are listed in terms of weakest to strongest. Okay, right. So all of these things were kind of talked about on the online, right? But to remind ourselves, right, to identify, right, if something has a dipole-dipole force, it has to do with the polar molecule. And so what makes a molecule polar? Is it that it has polar bonds arranged asymmetrically? Is it that the central atom with 2 or more different electron domains? Or 3, does it have polar atoms, right? And so think about this for a minute, and then I'll ask whether or not people think it's A, B, C, or D here. Okay. All right, so anyone feel strongly about one of these answers? Would like to share it? Say that.
D.
D. So you got someone here, central atom with 2 or more different electron domains and polar atoms. Okay. Let's talk about these things. Okay. So out of these things, so polar atoms, for example, polar atoms actually do not exist. Polarity for a given atom is not an actual thing. You can have polar bonds. So in this, right, instead of saying polar atoms, you'd have polar bonds. Okay? And polar bonds exist between 2 atoms that are basically not the same atom. They have different electronegativities. Okay? And every atom has a different electronegativity than every other type of atom. Some are much larger than others, right? So fluorine has a much greater electronegativity compared to, say, hydrogen. But hydrogen and carbon have very similar electronegativities. Okay? But every bond basically is polar as long as the 2 atoms involved are not the exact same atom. Okay? So if you have carbon bonded with carbon, that's not a polar bond because they're the exact same atoms. Otherwise, there will be polar bonds. Okay? And then central atom with 2 or more different electron domains, that has to do with types of bonding and things like that that might be involved in the atom, but will not impact its intermolecular forces. What you need is these polar bonds, right, that exist between different atoms, say carbon, hydrogen, or boron with fluorine or something like that. And you need them arranged asymmetrically. So what do we mean by asymmetrically? So we'll talk about that a little bit more here. Sharing screen, back to this. Right. So for example, okay, so asymmetrical, basically it's talking about spherical symmetry. Right. And so if things are spherically symmetric, then there is no polarity, or there's no polarity for the molecule. The molecule does not have dipole-dipole interactions. Okay. An example of this is methane gas. Okay. For this molecule, okay, if you imagine it in 3 dimensions, okay, right, you have like one atom popping out. This is how I draw these things in 3 dimensions or whatever, and one atom like going away from you, right? Okay. But if you were to picture this molecule in 3 dimensions, this thing is kind of, you could rotate it around in a lot of different ways, and it's going to look the exact same. It's spherically symmetric. Okay. Similar, right? Type molecules, you could have, say, xenon bonded with 4 fluorines in this kind of square planar type structure. Okay, or this thing would be spherically symmetric, right? What you can think of in these cases is each one of these bonds is polar. Okay, right? I'm going to draw these arrows to represent the polarity of these bonds. Okay, and each one of these molecules. Okay, these arrows, if you see in these two different examples here, these arrows sort of cancel each other out. If you were to try to like add up all the arrows, they'd all kind of cancel with each other. They all seem to be going in sort of opposite directions of each other, right? They would cancel each other out, okay? Now, an example of a polar molecule, I could have this exact same kind of structure here, but if instead I have a chlorine instead of a hydrogen there, okay? Now, chlorine is more electronegative than carbon, and so it's the polarity of the bond is more directed towards chlorine than it is carbon. And so now this arrow that up here, right, I have like a plus sign, you know, and then the arrow, right? The plus sign is at the hydrogen pointed towards the carbon. Well, now the plus sign is by kind of the carbon pointed towards the chlorine, right? And so now these arrows all have a net direction sort of pointing up a little bit, okay? And so this molecule is going to be polar because it has these polar bonds, right? These bonds here are polar and they're not symmetric. They don't have this spherical symmetry. There's some difference between these polar bonds in this molecule. So this molecule will be polar and will have dipole interaction. Okay. Dipole interactions, by the way, is probably the most difficult of the intermolecular forces to identify in a molecule. And again, a lot of it has to do with just the fact that, you know, being familiar with the structure and symmetry of a molecule can be sometimes annoying and takes practice. Okay. So in this question here, A, polar bonds arranged asymmetrically is what makes a molecule polar. Okay. Right, so then an example here, right, we have CCl4, Cl2, and CH2O. The question is, which of the following compounds can form dipole-dipole attractions between their molecules, right? It's kind of poorly phrased, right? But which molecule can form dipole-dipole interactions between other molecules of the exact same type, right? CCl4 with CCl4, Cl2 with Cl2, C2H, C2HO. Okay. And again, which one of these can have dipole-dipole interactions? So I've drawn out these three molecules here, right? So we look at these molecules, okay? CCl4, again, has the same type of symmetry as methane, right? It has these four bonds that are all polar, but they're all kind of pointed in opposite directions of each other. And so that's going to be spherically symmetric. And this guy will not have dipole-dipole interactions, okay? So not that. CCl, well, chlorine with chlorine, that's the exact same atoms bonded together. So those will not have any dipole-dipole interactions. That is polar, right? They're the same atoms. There's no dipole-dipole interactions there. And then finally, CH2O has this type of structure, okay? And this will have a net polarity that kind of points in the direction of the oxygen, and so this will have dipole-dipole interactions. Okay, this molecule is the only one of the three that can have dipole-dipole forces. Questions about this example? Yeah. Okay, I think I heard something over Zoom, but I didn't quite pick it up. Okay. If you have a question, again, feel free to ask it. You can always type in chat, hey, I have a question, if you'd like to ask the question as well, and you don't want to try to necessarily interrupt me, you can always type in chat, and I will pause once I see it to let you ask. Okay. Or if you're in class, obviously you can raise your hand. I'm happy to answer. All right. Okay, so this next question is related with hydrogen bonding. So I'll first let you decide which of these substances is hydrogen bonding likely to play an important role in determining its physical properties. Okay. And then through answering this question, we'll kind of also review a little bit about what is hydrogen bonding. And during this time, for those you know, who are in class, I mean, if you're watching Zoom with other people, then I guess you can also talk to them. But if you're in class, you're welcome to talk to other people around you about these questions and things like that. You don't have to work on it by yourself. The idea is for people to try to answer these questions, right? But again, you're welcome to work with those around you, talk with people and such, you know, while kind of discussing these things, okay? All right. So, can anyone tell me what makes a substance have hydrogen bonding? One ticket.
Open hydrogen is bonded with fluorine, oxygen, nitrogen.
Exactly. So in order to have hydrogen bonding, it's a very specific type of intermolecular force. It kind of is like dipole-dipole forces, but significantly stronger. Okay. And for hydrogen bonding, you have to have a hydrogen that's bonded either with oxygen, a fluorine, or a nitrogen. And then that hydrogen that's bonded to one of those atoms then can interact with lone pair electrons on other molecules. Okay. And so, for example, in here, I have these different examples in order to give us some practice on seeing some of these structures and kind of drawing them up. Oops. F, well, H. I'm just drawing the structures real quick here. G, H, H, and S. Sorry, my handwriting here is going to be a little bad, but okay. So these structures here, that can help any, maybe. The zoom on this, or the focus on this is awful. 4 plus, okay? So this does have nitrogen and hydrogen bonded together, right? There's nitrogen-hydrogen bonds, okay? But when this tries to interact with another NH4 plus, the hydrogen doesn't have any like lone pair on this nitrogen, for example, to interact with. And so this will not have hydrogen bonding, okay? Oh, not star, right? This will not have any hydrogen bonding because that the hydrogen bond to nitrogen needs to interact with, say, a lone pair. But in this example here, I have this nitrogen-hydrogen bond, but the nitrogens will still have these lone paired electrons. So what will happen if you were to draw two of these things interacting with each other? So I'm just trying to draw out two of these molecules here. All right, move that up here, right? So I have two of these molecules, right? What will happen is you have this nitrogen bond with this hydrogen, and then that hydrogen is also interacting with the lone pair on another nitrogen nearby, okay? And so basically, typically the only example where hydrogen bonding doesn't exist when you have hydrogen bonded with another nitrogen, or at least an example given in this class, is basically this NH4 plus, okay? NH4 plus is one of the few instances where you have a hydrogen bonded with a nitrogen that you wouldn't actually have hydrogen bond, okay? But typically, if I have hydrogen bond with a nitrogen or an oxygen or fluorine, there's going to be some lone pairs floating around somewhere on those oxygens, fluorines, or nitrogens, so you will have hydrogen bonding, okay? Now, this molecule does not have hydrogen bonding because even though it's written as CH3F, the hydrogens aren't bonded with the fluorine, right? They're bonded with the central carbon, which is what the fluorine's bonded to. So there's no fluorine-hydrogen bonds in this molecule, so there will be no hydrogen bonding. And then the last molecule has sulfur hydrogen bonds, which will not undergo this type of hydrogen bonding in molecular forms. Okay. So out of this example here, right, B is the only molecule that has hydrogen bonding that will play a significant role in its intermolecular force. Okay. Questions about this example? All right. All right, and then this third example here has to do with dispersion interaction. Okay. Dispersion interactions, also sometimes called London dispersion interactions or van der Waals forces. There's kind of three different names that sometimes are given, depending on who you talk to. But here I'll typically use the force dispersion interactions, dispersion forces, right? Dispersion forces happen between all molecules. It's the weakest type of intermolecular force, but it exists for everything. Every molecule and atom has dispersion interactions. Okay? Helium atoms have dispersion intermolecular interactions, intermolecular forces between other helium atoms. Okay, it's why helium can be condensed down to a liquid or potentially solid, because it does technically have these intermolecular forces. It is extremely weak, so to get helium liquid, you have to go down to like 4 Kelvin or something like that, like extremely cold temperatures to get it to condense because these forces are so weak for helium, but they are still there, okay, for every molecule, every atom. And these dispersion interactions are what are called like induced dipole interactions, right? They exist in every molecule, but they're more relevant in larger molecules, okay? Because the larger your molecule is, right? So these interactions have to do with electrons kind of fluctuating on molecules and creating temporary dipoles, and those temporary dipoles interacting with other temporary dipoles. Okay. And so the more electrons you have in your molecule, the larger the molecule is, the more electrons there's going to be, the more dispersion interactions there will be. Okay. Because the more these electrons can move around, the larger dipoles that can be created and things of that nature. Okay? And the other thing that can affect these dispersion interactions, right, is if they're planar or spherically shaped, right? If you're planar, you have more area of interaction between your molecules than if you're spherically shaped, okay? Right, and so for this example, which of these molecules will have the highest melting point? So the first part to this question is let me say this a different way. To have a higher melting point, your intermolecular forces need to be stronger or weaker? Stronger, right? Your intermolecular forces need to be stronger to have a higher melting point. So this question is asking which has the strongest intermolecular force, okay? All of these molecules, okay, their strongest intermolecular force is going to be dipole-dipole, or not dipole, sorry, dipole. Dispersion interactions, right? The strongest intermolecular force between all these molecules is dispersion. Okay. So out of these, which molecule will have the strongest set of dispersion interactions? It will be D here, hexane, right? Molecule here, hexane. Hexane will have the strongest set of dispersion interactions, and this is because it's the biggest one. It's the biggest thing. Okay. These dispersion forces are very significant. Okay. Polymers, a lot of polymers are held together through dispersion forces. Even proteins and things like that, dispersion forces play a significant role in their structure and how they're held together and things like that. So again, as you get to larger and larger molecules, these dispersion interactions become more and more significant and more relevant. Okay. But they do exist for every type of molecule, but they are the weakest intermolecular force, right? Again, right, in terms of strength, dispersion are the weakest. They exist everywhere. Dipole-dipole are the stronger in dispersion, but they only exist for molecules that are have polar bonds and are asymmetrically arranged. Okay, hydrogen bonding is stronger than dipole-dipole dispersion, but hydrogen bonding only exists for molecules that have hydrogen bonded with fluorine, oxygen, nitrogen, right? And then ion dipole, which we haven't really done an example of, right? That's just interactions between polar molecules, like those that exist for dipole-dipole interactions with a charged species, right? NH4 plus, Cl minus, Na plus, right? Ions in solution. Ion dipole forces basically are the reasons why salts like sodium chloride dissolve in water. Okay? Because the intermolecular interactions between the sodium ions and the chloride ions, and then the water molecules, the dipole interactions within those water molecules. Okay. Right. And if I want, so this flow chart here sort of ignores ion dipole forces, because again, ion dipole forces only happen when you have a ion and a polar molecule together. So it's fairly straightforward to identify those. You have to have two different molecules, and one has to be charged, right? But so ignoring ion dipoles, right? For most examples, we deal with this type of flow chart is what I like to use to identify what intermolecular force is most relevant. Okay? And the very first thing is I ask, is hydrogen bonded with a nitrogen or chlorine? If yes, then there's hydrogen bonding. If no, then we go next to whether or not there are polar bonds. And if there are polar bonds, are they arranged asymmetrically? If yes, it's dipole-dipole forces that are strongest. If no, then it's those dispersion forces that are going to be the strongest. Okay? So an example here can work with yourself or with other people, right? And we'll do lots more examples of this of this type of stuff on Wednesday and whatnot. But question here is what type of intermolecular forces would be most significant for these molecules? Okay. You also have any questions? I'm happy to answer those right now as well, while people work on this. A question to see that chart again. So this, I'll go back real quick to the chart, right? This chart, freeze this screen, those who, right? I froze the screen in class, but I'm pretty sure on Zoom you see not the projector, but what's on my screen here. So you should be seeing the flow chart on Zoom real quick. But this flow chart online already, the lecture slides online have that flow chart there, as well as a number of these examples. Okay. So I'm going to go back, example, unfreeze that screen. All right. So for this first molecule here, right, this CH3OH, okay, what is the strongest intermolecular force for this molecule? Hydrogen bonding, right? I have a hydrogen bonded with an oxygen here, so there's going to be hydrogen bonding. Okay. Right? That's the strongest intermolecular force for that molecule. For this next molecule, CH3OCH3, okay, didn't draw it the best, but what will be the strongest force here? Dipole-dipole, okay? I didn't draw it too properly. Really how this looks is you have an oxygen with carbons kind of bent down like this, sort of like you would look like a water, and then, you know, the hydrogen's here, right? And for this molecule, right, these carbon-oxygen bonds are polar, where the polarity is kind of pointed towards the oxygen, so you have a net dipole moment kind of pointing up here with how the structure is drawn. So these have polar bonds, right? These carbon-oxygen bonds are polar. They're not going to be symmetric, okay? It's not a linear molecule. It's not some sort of spherically symmetric molecule, as an example we'll see in a minute. So this has dipole, right? And this next molecule, CH3Cl, right? Dipole as well. And then finally, CCl dispersion, right? Okay. The CCl4 does not have hydrogen bonding, and these polar bonds are arranged symmetrically, so it's not going to have dipole-dipole, so it's going to have dispersion interaction. Okay. Questions about these molecules, about identifying these forces? Yeah, yeah, yeah. So just like CH4, where it'll be arranged symmetrically, the CCl4 as well. Okay. All right. Then let's just do another example here real quick, right? What is the dominant intermolecular force in a sample of acetic acid, CH3COOH? The structure is given here in the slide, right? The strongest force is going to be ion dipole, hydrogen bonding, dipole-dipole, or dispersion. So we'll have dispersion forces. Anyone think it will have anything else?
Dipole.
It will also have dipole-dipole because it's got polar bonds arranged asymmetrically. And then what's going on the right side of the molecule here?
Hydrogen bonding.
Yeah. So there will be hydrogen bonding in this molecule because it's got an oxygen and hydrogen bonded together. Okay. So B here, the strongest, the dominant force will be hydrogen bonding, but it does have dipole-dipole interactions and it does have dispersion, right? But again, so typically that's why these questions will always ask for what's the dominant, right? What's the strongest force that exists for this molecule? Because something that has hydrogen bonding is going to have dipole-dipole and it's going to have dispersion. Something that has dipole-dipole forces will have dispersion force as well, but again, those are weaker forces, right? And so that's why we typically ask for the strong. Okay.
Okay, I have a quick question. Why exactly is it? Could you go over why exactly it's hydrogen bonding, like, again?
Yeah. So in this molecule, there is, right on the very right side here, this oxygen and hydrogen are bonded together. Now, how it's drawn, it doesn't draw like a line between the oxygen and hydrogen, right? But they're written next to each other right there, bonded together. And hydrogen bonding exists whenever you have a hydrogen bonded to oxygen, nitrogen, or fluorine. Okay, and then there are like lone pairs on those oxygens, right? Or nitrogen and fluorines, which again, the one example I gave that like NH4 plus is the only time where it doesn't exist in things we'll talk about in this class. Okay, but otherwise, besides NH4 plus, right? If there's hydrogen, oxygen, or hydrogen and nitrogen, or hydrogen and fluorine bonded together, those will have these hydrogen bonding forces. Okay? And that's why it's called hydrogen bonding, right? Because it has to deal with hydrogen bonded to either nitrogen, oxygen, or fluorine. Okay.
All right, thank you.
Mm-hmm.
So
Yep.
you said it has, unlimited and
Mhm.
isn't dipole-dipole like related to polarity or?
Yeah, and this molecule will have polarity because I mean the structure is not written how to be in 3 dimensions, but the structure here, this carbon oxygen bond, for example, is going to be polar, and it's not going to be canceled out by the polarity between like this carbon oxygen bond and this carbon carbon bond and things like that. So the structure of this guy, it's going to have polar bonds that are arranged asymmetrically. Basically, the type of symmetric structures you'll deal with in this class are things of the structure like methane, CH4, or that CCl4 structure. Those will have polar bonds that will be arranged symmetrically, or linear molecules. Okay, like right, like CO2 or things like that, where you have things arranged symmetrically. Okay, but typically, otherwise you will have any structure that has polar bonds, right? Are typically going to have kind of dipole-dipole interactions if they have things like difference in electronegativity. The other examples are when we talked about these molecules here, these carbon hydrogen structures. These are typically going to have dispersion forces are their strongest intermolecular force. Okay, because the polarity between the carbon hydrogen bond are very weak, and these directions of these bonds typically cancel out with each other. In these carbon hydrogen structures, they won't have dipole-dipole force. But in structures with oxygen thrown in with carbon and hydrogen, like this acetic acid, they will have dipole-dipole forces. Right? It's just that in this case, you also have hydrogen. Again, we'll do more examples of this on Wednesday as well. Okay. But I will, so to kind of wrap up at least for today, right, again, if anyone decides they don't feel comfortable attending class, talk to me about going online. Right, these sessions, I'll typically try to fill up, for the most part, the lecture sessions with plenty of examples and discussions and things like that. But I will try to end a little early so people have time to leave without having to bunch up at the door while you're leaving. Okay. But yeah, and then I'll post these Zoom lectures, these Zoom sessions on YouTube as well. Okay. So we'll continue this discussion on Wednesday. Okay. Again, you have to get through the right here. You know, I encourage people to please not bunch up as you're exiting. Take your time. Still leave when you feel comfortable leaving. But yeah, otherwise, if you have questions, I'm happy to answer them. Then I'll see you next week. Oh, you're right. Thank you. For the questions, just put them on the table as you're leaving through the door. Okay. So you can just set those in on the table by the door as you're leaving, and I'll pick them up as I go. Okay.
Professor Yoss.
All right. Oh, yeah, here. So for those who are still here on Zoom, that's sort of the end of the class. If you have questions, I can answer them real quick while people are leaving the classroom and such. But otherwise, I will log off of Zoom in just 1 minute if there are no questions. Okay?
I had a question.
Email earlier saying that I couldn't find my name on the
Yeah.
Monday group for the Wednesday group. I checked the one in files and it had my name on it.
Okay.
So don't worry about
Okay.
Thank you, though.
I see you Wednesday then.
I didn't know how the group A and B were, so I'm group B.
Okay,
Showed up
that's
today,
fine.
like,
Yeah, yeah,
Wednesday.
yeah, that's fine. Yeah,
You turn them in?
yeah, I mean, I can take them here, but yeah, otherwise, just
Oh,
typically it's the thing we're using. So.
I have a question about the sampling. If I bought the like bundle from the bookstore, does it come with like the sapling card, or do I still need to buy the sap? Like,
I don't know exactly what's with the bundle, but I'm sure it comes. How much did you pay for that?
$100.
Huh?
$100.
Are you able to return things?
I hope so. I
Because
don't-
yeah, I would suggest
I mean,
just going
it's
directly
like
through
intro
sapling.
textbook.
Yeah, because I think it's like if you just get it through sapling, like it's
cheaper.
cheaper.
Okay.
So I would suggest looking to just do it through sapling
All
and
right.
through the bookstore. Like we have to put these things on the bookstore, but then at the beginning of every semester, all the faculty always say like, I suggest using other things besides the bookstore to buy stuff because it's typically cheaper. But,
Okay.
All right, thank you.
So we come to in-person. Sorry, I was late.
Yeah, that's fine.
I was walking around Centennial and I was at Centennial 100 and I was like, but so we come to class on Monday and then we watch the lectures on Zoom on Wednesday.
Yeah.
Sounds good.
Yep.
Thank you.
No.
Oh, okay.
Was that probably when this was originally created? The
Well, so listen, say this argument.
yeah. So we don't need clickers. Hopefully they aren't on like at the bookstore saying it's required for the class or something like that. Because when the class was first set up, like before all this crap happened, there typically are clickers required. But yeah, you don't need to purchase any clicker devices or anything like that. So the only money you need is the sapling thing, which comes with the online.
And I guess sadly, yeah, and when we did it, because I thought this is called the integrated, like it's the first group integrated and then on the second interactive. I don't know if that's what
Oh, that's just a typo on my part. It's the same
okay.
thing. Yeah.
Oh, okay.
Yeah.
Gotcha. I think so.
Yeah, no problem.
I have a couple questions.
Yep.
Okay, when you say spherical symmetry, is it like the Vesper, like the VSPR?
I'm trying to remember the best.
Like the lone pairs and the bonding in the region?
Yeah, I mean, so you can kind of work out the symmetry through that. But again, like I'll say this class, I like hopefully you don't have to recall and remember all that. Like again, basically linear type molecules potentially have the right symmetry to not be polar, even if they have polar bonds. And then basically like carbon with 4 things attached to it, if they're all identical.
Yeah, like the planar.
Yeah. So yeah, or that XE like F4 example I gave or something like that. But yeah,
And then, when you say electron domain, like, is that the bonding region?
yeah. So that was related with kind of like like the bonding regions and Vesper and other things like that. But again, that was like a throw off thing. That has nothing to do with whether or not things are.
So like electron domains, can they be a bonding region or is it just lone pair?
Two or more different electron. So two or more different electron domains would be like if it's bonded or if it has a lone pair or something like that. But again, that actually has nothing to do with whether or not it's.
For NH4 plus, isn't that ammonium?
Yeah. Mhm.
Is it not hydrogen bonding because it has no lone pair, so it
Yeah.
can't?
Yeah, because the hydrogen technically has to interact with the lone pair, and that's the only time when hydrogen bonds with the nitrogen oxygen where the molecule doesn't actually have a lone pair.
Is it,
And-
is it also kind of because it's an ion?
Yeah, I mean, and it's an ion, so it mixes things up as well, whatever. But yeah,
Okay.
yeah. So there's a lot of reasons why.
I was gonna ask, is there any way that you can show it Monday and
So show up both days, is that what you're saying?
Yeah.
I mean, I wish you could if you wanted to, but like the campus policy is for classrooms have to be 50% occupied, and we're supposed to have a class. Yeah, I mean, if let me touch. sharing that, and let me end session. Goodbye.